So I want to start by highlighting a problem on quantum observations. Uh, so let me say the way I am thinking about these lectures is not to go into technicalities on algebraic quantum field theory, which can be done, but in a set of talks of 6 or 7 talks, it is impossible, especially because one has to have a broad background as a preparation. So my idea is to highlight certain issues, and then if there is a strong interest in knowing something more, we can have special sessions, or we can discuss. Somebody here was talking to me about a thing like half-sided modular inclusions. That's a very technical subject, but we can discuss and we can learn together what it is. But we can, for that, we can arrange separate discussion sessions to go more deeply. But now I want to cover what are the motivations and the kind of results which are coming out, especially as they impact on the standard quantum field theory activities, which are really have a strong classical clutch, and they are coming from classical theory. So here we are trying to somehow liberate ourselves from that prison and go in a new direction. Let us see how far we can go. So in order to highlight the problem once more, of what is the problem in quantum observations, let me point out to you that if we are working on in the standard formulation, we are working on some Hilbert space on which we have certain linear operators which we observe, experimentally we observe. But one should remember that if you have a finite dimensional vector space, complex vector space, for example, Cn, what is denoted by Cn, there is only one, all finite dimensional complex vector spaces with dimension n are the same up to isomorphism. There is no difference. You can map one to the other, preserving all scalar products. So there is no distinction whether you prefer to work on a lattice of dimension n or write it as a column vector or do whatever else you want to do. There is no difference. You can do one or the other. So the only invariant object in finite dimensions is the dimension of the vector space, at least in finite dimensions. Now, what happens in infinite dimensions? If I make n go to infinity, what happens? Well, in infinite dimensions, what we normally deal with are, somebody is trying to come. Yeah. In infinite dimensions, what we try to do is to work with the Hilbert spaces which have a countable basis. Okay? So, for example, we take harmonic oscillator and it has a basis consisting of Hermite polynomials, which is countable indexed by integer n. Or you might have something else, say hydrogen atom, which also you can arrange to have a countable basis. So whenever you have a countable basis like this, what you get is what is called a separable Hilbert space. That is what we normally deal with. These are not the only Hilbert spaces which can turn up. There are so-called non-separable Hilbert spaces, which come in loop quantum gravity, for example. But for now, we will only deal with separable Hilbert spaces. But yeah.
Aren't all Hilbert spaces isomorphic?
No. So the only invariant of an infinite dimensional Hilbert space is what they call the cardinality. Okay? So it's a question. So if you have a countable basis in infinite dimensions, then all such Hilbert spaces are isomorphic. Not only they are isometrically isomorphic. You can map one to the other, preserving the scalar products. There is no difference. But this tells us, and what we are observing are linear operators on this Hilbert space, but they are all the same set. Whether you write it using Hermite polynomials of the harmonic oscillator or the wave functions coming from a hydrogen atom, they are all the same. The linear operators can be put in one-to-one correspondence.
So this is not true for non-separable.
So they have. So if you go into non-separable spaces, their structure is quite different. There is no such isometric mapping. Typically, in a non-separable Hilbert space, or the kind I know, what happens is that there is no Okay, if you try to reduce it with regard to the algebra that is acting there, then it is a direct integral which cannot be decomposed into a direct sum. And each fiber is also orthogonal to, for example, I'll give you an example. Take the paramagnet and all space point in that way. Okay? That gives a Hilbert space, and don't change the spin at infinity, that gives a Hilbert space. You move it a little bit, you get another Hilbert space for that direction. Now you ask, can I take the direct integral over all these directions? You can, but then vectors in one direction Hilbert space, in another one will be orthogonal. Not delta function, they will be orthogonal. So even if you go to the limit, you will get zero. So that is not what we get. In the separability, that's not what you get. You get some continuous interpolation. So basis vectors are really out. So if you take two orthogonal vectors in a separable space, you get always zero. Okay? Here you will not, because there are the topology of this case, even infinitely near objects are orthogonal in the Hilbert space sense. So it's quite different. So I don't know the theory of this not separable spaces. Only I know a little bit as so far as they come in physics, but there is some literature. I don't know it. I have not been motivated to study. Okay. So going back to Hilbert spaces, all separable Hilbert spaces are what we normally deal with. And all the infinite dimensional Hilbert spaces are isomorphic. So I can do if I want to just to tell you, harmonic oscillation or a line, I can say I will not work with functions on one variable and do the calculation. I'll represent the whole thing in 3 dimensions. I can do it. It will look very complicated, but there's an isometric mapping, so you can take all the operators in one and put it in the other, including the Hamiltonian, everything you can put there. And redo the calculation, you get no difference. In fact, Dirac has done his calculation for the angular momentum without ever telling in an abstract way. He didn't write the Hilbert space for the angular momentum by writing basis. He just had an algebraic way of doing the whole thing. Now, that raises immediately a problem, which we brought up in 1997, I think, entitling a paper which you can access in the net, and it is titled Bringing Up a Quantum Baby. So the title of the paper is How to Bring Up a Quantum Baby. So we were very concerned, since we are all quantum, the babies are also quantum. So, and they're going to grow up that quantum. I suppose their parents are very decent people. So they will treat it on unbounded self-adjoint operators on a Hilbert space, all of them, okay, and it will grow up, see those things. Then how when it grows up, how can it tell a hole in the ground from a donut or something? It cannot, because it is taking all the operators, measuring all the operators. So it will know about self-adjoint operators on a Hilbert space, but how will it know? How will it distinguish? Let us say, as I say, a hole in the ground from a vadai or something like that. How will it know? How will it? How will it overcome? No, I should say, necessary education of being a quantum baby and growing up as a quantum child. And I suppose all parents are very decent people, so they will make sure that the child is quantum and doesn't become classical. So what happens? Well, being very socially minded people, he gave some instructions on how to do it, that paper. So those who are interested can browse through it. So let me go on. Okay. So this is the problem. This is another aspect of the problem of quantum measurements. This does not happen in the classical system. So okay. So I wanted to bring this up. I don't think it is a trivial issue. You can have a look. Okay. So let me recollect what we did earlier. Yeah. Our starting point last time was that in the classical physics, they are also in quantum physics, a description of any outcome, any observation consists of 2 parts. Okay? First is the ensemble being measured, okay? And it is given by a probability distribution rho in a phase space. It can be a delta function for a sharp observation, or it could be actually a distribution, whatever it is. But this is always the case in classical physics, as it is in the quantum case. Then there are things we measure, and the observer and this set of objects we measure, the observables are functions in that case on a phase space. So the result of the experiment, as I said earlier, these two have no separate existence. These are joint that has a meaning. So the mean value of f, that is what we register experimentally. It is this possibility that allows you to let me go on. The same thing happens in quantum mechanics. In quantum mechanics also, there is first a state which is telling you what is coming to you. For example, in the ring, say in the CERN ring, what is coming to you, that state of the system is described by some density matrix. And we make the experimentalists who is setting up the lab, who is doing the measurement, is selecting certain events, which is what is being observed. So it is describing some operators. Now, in elementary quantum mechanics, what we do is to represent the vector by a vector in Hilbert space. Okay. I have not told you where that comes from, but let me now just tell what we do normally in elementary classical quantum mechanics. We take a wave function in the Hilbert space, and we say that the outcome of the experiment is the mean value is going like this. Okay. This is what we normally do. First thing you should observe right away is that all that we have access to is the last line. The rest is our theoretical description, and we have no. It is necessary to. I mean, Einstein himself has said that the elements of theory are not necessarily those which are accessible to experiments. Okay? So we have access to a free imagination, which we are happy, and this is what we do. The end result is what I got to. Okay? That's what we get. This, by the way, to some of you, this will tell you that since the separation between a state and an observable is not sharp, you have the possibility of dividing, putting lines as to where the system ends, the state ends, and where the system starts. And this ambiguity is what lets you have these various representations which they like to recognize, like interaction representation, Heisenberg representation, and so on. He recognized it because he realized that this division is not sharp, but it is not stated in his book. But I think the people like him and Schrodinger must have realized it right away. That's side remark. But the major remark here is that this whole thing to me looks very artificial. The artificial is that in classical physics, there is no trace of Hilbert space. Where is this Hilbert space coming from? I don't know. Some people mumble to you about wave particle duality, and there is some stuff like that. Then after a while, you find that this doesn't quite work because, for example, on a particle on a circle, you don't have position operators. So what do you do? Then there is a long, at least in some places, a long discussion on how to overcome this problem. They tell that they give various excuses. Then you get something else where you cannot do this. So this business of wave particle duality is to a large extent systematically brainwashing the students to accept what we are doing. Okay? There is no good way of understanding it in a, at least I had no good way of understanding it from my beginning days. So you got to get used to it. Okay? Getting used to it is not the same as accepting, but now I think they have a better way of looking at these matters. Okay. That's statement number one. Okay? So, a related problem with this wave function is that wave function is not uniquely defined. I can multiply a wave function by a phase, and the mean value is unchanged by multiplying the wave function by a phase. So the wave function is not defined by itself. There is a whole class of wave functions, all multiplied by a phase, which give the same state. So in fact, we can say that what you are getting is a ray in the Hilbert space. Okay? So the correspondence between wave functions and states. State for me is that rho is what I call state, not wave function. So if I call psi as a wave state, I will call it as a vector state. to distinguish it from a density matrix because they're not exactly the same. Okay? So we will always deal with density matrices, and you see that the mapping from wave functions to density matrices is not inject, is not one. There are many wave functions that give you the same density matrix. And if you try to go backwards, you don't get the wave, you don't get unique values. Okay, so this is a starting point here, and this point was already noted in 1931 paper of Dirac on magnetic monopoles. That is a very remarkable paper. Yes. If you read that paper, first it's not all. Let me say, to read it, it's a very beautiful paper, but not easy to understand. It is very clear from that paper that he realized that wave function intrinsically has no meaning. In fact, he is trying to describe the charged monopole system, and he attaches phases. That is, he attaches Wilson lines to wave functions, and he says that you can never see. And he does not articulate this fact, but it seems to me that either he knew it or he was very near it. And then he got already in that paper the remarkable result that the charged monopole system can be quantized only if electric charge times magnetic monopole charge, Eg, divided by 4 pi is quantized. And he proceeded to give this as an explanation of why electric charges are quantized. It's a very remarkable paper, and I suspect that Schrodinger as well was quite aware of these facts. In fact, I think Schrodinger was a very remarkable person. For example, already in 1938 paper, which we traced much later than our own work on the ambiguities of density matrices and entropies, he seems to have realized it because there is a whole paper where he gives systematically why why entropy is not a well-defined quantity in quantum theory. He discusses it in 1937, 38, something like that. He discusses it. By way of a story, I was in Dublin. There was a play. There was a play about Schrodinger. During the war, you people no doubt know that Ireland was neutral. What is the result of his neutrality? All the spies from all over the place, Germany, England, Russia, they were all there, and just completely crowded apparently with spies. Why were these people there? Well, Schrodinger was working in the DIAS, in Dublin Institute for Advanced Studies, and there was a rumor going around that he had discovered a great machine which they all wanted to get rid of. What is that machine? Just called the improbability machine. What is an improbability machine? It will invert a wave function. So the rumor was that he has a machine which will invert the wave function. So they want to get it because the least probable event will become the most probable by inverting it. So they were trying to catch Schrodinger, but Schrodinger was off somewhere in some mode. Somewhere he has gone off. So that's the story. The whole story is evolving around this play was revolving around this fact. Not only it is true, because Schrodinger had so many, he was also giving this talk on what is life there at that time, and this fantastic little book on technique. So there is no doubt that he was a very gifted person. So that's by way of entertainment. Okay? So in 1931 already hints were coming that the role of, for example, role of density matrices is much density matrices quote much more information than do states, or at least that way of thinking. For example, Wigner already there, starting from the observation that any symmetry in quantum theory need not do anything on wave functions. Okay? What it has to do is to preserve the state of the system. He started analyzing this information. In fact, that analysis is highly epistemological. He's analyzing what kind of activity will preserve probabilities. Then he found out in that analysis that by choosing some irrelevant factors, either that operator which is acting on quantum states rho can be lifted either to a unitary operator or an anti-unitary operator. So that analysis is highly non-trivial, and as recently as 10, 12 years ago, there appeared papers by Mukunda and I think Simon here, and also by Sam and RRI, trying to get simplified simplified proofs of that theorem. Okay. So that's a fundamental theorem on how to lift symmetries from density matrices to the Hilbert space, and Victor had discovered it already in 1931. And the anti-unitary operator, which has no trace of, I know of no trace of the classical theory, happens here because we are dealing with states. Okay. Then in 1939 came this remarkable observation about rotational symmetry by Wigner. Again, this is very highly non-trivial, and it comes because we are dealing with density matrices. He pointed out that a 2-pi rotation, well, 2-pi rotation should do nothing. It does nothing. If I stand here and I rotate by 2-pi, just rotate like this and go back to my original state, I've done nothing. Nothing can change by doing this. Victor pointed out that this is okay, but when you lift it from density, so the density won't change. But when I lift it to wave functions, it can change by sign. Okay? So he made a very fundamental analysis of this phenomenon. And now we know that it is very basic to things like spin statistics theorem and all of magnetism. All of magnetism with condensed matter is relying on this fact. So all these facts are already known in 1930s, late by 1930s, but they somehow went into limbo. People did not follow it up until I think then also came Wigner's 1939 analysis of how to go away from Lagrangian field theory, and at least at the particle level, how one can write all the representations which are compatible to unitarity and anti-unitarity of the Pompey group, which is necessary by requiring that the density matrices are preserved, and how they can come directly from an analysis of group theory. So he had classified the whole damn thing, that all the representations of all possible particles already in 1939, including one which nowadays sometimes people call continuous spin representations, which he wrote down. But how to write quantum fields for it, which we will be dealing with, will come later to that. We understand that now, certainly for all the massive particles, and for massless particles, again, there are problems. But we know, for example, Weinberg already showed in his book, he has shown it, that for massless spin one particle, like photon, there is no such thing as gauge invariance in the representation of the photon. But if you try to write a quantum field for it, there's a problem, some problem in writing intertwiners, and Weinberg already discussed it. Okay. So the transition from Victor representations of particles to quantum fields is highly non-trivial. For massive particles, it is more straightforward. For massless particles, the story changes. Okay? And some of the issues there, just to tell you what it is, in the Wigner classification, there is a particular massless particle whose little group is the Euclidean group in 2 dimensions. Okay? And it has those representations it has finite dimensional representations, and they give you massless particles with spin 1, 2, 3, and so on, okay, like gravitons and higher spin particles. But it also has representations with all possible spins. Okay. Nothing wrong in their physics. They have positive energy and nothing wrong in their physics. But people failed in writing quantum fields for it because of this problem that Weinberg raised in his book. He didn't consider this, but people doing algebraic quantum field theory realized that standard techniques for writing the quantum field simply doesn't work. And it has been resolved only very recently. So this is where I keep talking about strictly localized fields and just being resolved, apparently resolved. Only very recently, less than 10 years, by again Mund, Schroer, and Ingvarsson, they have given a solution and they have discussed this issue. So something very fundamental is going on in the transition from in the quantum theory from our interpretation of quantum states in the Hilbert space to a quantum field. This does not happen in classical physics. So this is a strong contrast between classical and quantum physics. So I think this time, if we want to discuss fundamental physics, we try to wean ourselves away from Lagrangians and stuff like that. At least try. Okay. They can limit our visions on what are the possibilities. Okay. So there are questions, please ask it. So all this suggests that it should be possible to formulate quantum theory purely using a states omega on an algebra A. So algebra, yeah.
Except that from classical, from let's say, let's say, how does that go? Consider people from
Classical physics, how do you prove there are only two polarization? I mean, experimentally, I'm not asking, of course, photoelectric effect will show it, no? But we don't know that the photoelectric effect is describing the same object as what you see in light switch. Okay? We don't know it. It came much later by work of Einstein, okay, and people like that. But how will you describe it classically? I don't know. Maybe.
possibly it can be wave, let's say, it's propagating the dimensional space which one transversal direction that, you know.
How do I tell that that's a particle? Particle is something localized, no? At least that's what we understand. So this is the photoelectric effect problem, no? If I have a wave hinging on a plate, and if it is a wave, energy is spread out, and then you will not have sharp signals. But experimentally, they saw sharp signals, in the photoelectric effect. This h nu minus omega formula. So that immediately posed a problem. What's happening? And Einstein was the one who resolved this funny experimental fact that I know. Okay? And later it led to Bose's work on Bose-Einstein statistics. And it went in a, so that is the beginning of this fact that this classical description was inadequate. Maybe there is some way of revolving it, getting around all this thing classically, but I don't know how. Maybe there is. We have to think. So in the 30s, 20s, the photoelectric effect emerged in the 20s, if I remember correctly. And the problem with this duality, the experimental results on photoelectric effect emerged around that time. Okay, from what I know. So, what happens here? So, in quantum theory, we deal with operators like position operators or momentum operators. I have put them a hat on these operators, but I prefer to work with the exponential version of this, which are unitary operators. So there is no problem, technical problems like a commutator of x hat and p hat having a non-manifold trace. So, that immediately challenges our intuition on what is meant by a trace. So there is this algebra A, and the state assigns a mean value to the algebra, as I have said many times. So omega is a state, and if I take experimentally measure some operator from A, I get a complex number, which has the property that on the identity of the algebra A, I get 1, so that the total probability is 1. And I should also have this, since I want to pretend that omega is a probability. So this algebra has something called a star operation, which is like Hermitian conjugation, but can be defined without talking about Hilbert spaces. We can define what is meant by alpha star without referring to Hilbert spaces. There is some star operation. So, and I want omega to be alpha star acting on alpha star alpha to be non-negative. Okay. So this is the requirement that it is a positive. It has the properties of a probability distribution. Okay. So So meanwhile, for example, an operation like alpha, if we trace of rho times alpha. So rho is, I'm representing the omega as a rho. You may challenge me how do I know there is a rho? Um, there are two answers, but we will actually find the analog of the rho in a minute. Purely intrinsically, but I learned only a few days ago that there is actually a theorem due to who? Kolmogorov, sorry, I don't remember, that they prove that this can be done always. So at least for a class of state, it appears that it is possible. Some review, some classes given by Gleason, I'm sure that Sivashish knows about. He discusses this theorem and quotes a reference, but I have not gone through the book. Okay, so if I do like this, it looks much closer to what we do in classical physics, where this omega is represented by a certain integral, okay? And trace becomes an so what is written as trace here becomes an integral on dpdq. Okay? So that is quite natural. Okay. Yeah.
That's fine. The question is even the measurement statistics of the quantum system. Can I immediately identify this state omega?
No. I mean, how many, like the question should be, how many measurements should I do to recover the state omega infinity?
Let's say I have sufficient number of it.
The answer is I don't know, but I know that your colleagues in Hyderabad, like Subhash Chandra, K.R. Parthasarathi, all those people, have been working on what is the minimum number of measurements to it.
Question of language.
Okay. Yeah, if you make a subject number, yes, because that is what defines omega. Omega is defined. There is no independent existence of omega. So if you give me sufficiently large number of numbers table, then of course that is omega. So if I think of omega as a big huge table, if I think of it like that, that is we are thinking, but may not be useful experimenting. Or in some infinite dimension, there are so many operations. So we don't, since a finite dimension system, maybe it's useful. Yeah. But this is what the minimum number of measurements to recover role. These are problems which come in quantum engineering. I don't know the answers, but there are people like Subhash, ex-Hyderabad, K.R.P., some others, they are thinking about this, but I don't know. I am not familiar with it. Okay. Okay. So, anyway, I think this, to me at least, this looks closer to classical physics. But then, in this language, the only difference between classical and quantum physics is that one case, the algebra of observables commute. Their point-based multiplication, they commute. Whereas in quantum theory, they don't commute. This is the only difference. But from this difference comes all these problems I told you, including the problem of the baby, the quantum baby. So how do we resolve it? So, so the point of view that is emerging here is that quantum physics is nothing more than a non-commutative probability theory. So, but then the issue arises, where is the Hilbert space, which we start our game? That is how textbooks like Messier or Jackson or somebody, not Jackson, some other textbook which we teach started. Where is that Hilbert space? So, I would say the extraordinary discovery of how to recover the Hilbert space from this data, from a state on an algebra coming from Geffen and Neumart, and later adapted to quantum theory by Irving Siegel, are quite extraordinary and quite fundamental. And somehow they are dominating this algebraic quantum field theory. As recently as a few days ago, there appeared a paper by Roberto Longo, and I noticed, and he is discussing how to define entanglement entropy intrinsically in quantum theory. And it is all dealing with these states and algebras. And he also refers to a paper by Aligon and Moscovici, where there seems to be a claim that they have found a quantum mechanical system, the spectrum computed using such techniques for a large eigenvalues are, let me put, remarkably close to the zeros of the Riemann zeta function. The paper looks like they are claiming that they are very near the solution of the zeta function zeros. So things are happening. As you are sitting here, things are happening and evolving by themselves, and we should at least be aware of it, in my opinion. So let me come back to this. And how do I find from the data a state and an algebra a Hilbert space and the representation of this A as operators on this Hilbert space? Okay. That is the issue I want to discuss here. The work I have done here were done with some people like TRG Govindarajan and two visitors at that time, Amilcar Queiroz, who came here from Brasilia, and Andres, who came from Bogota. They were here for a few months, and we worked on this problem. And later we continued this thing and also did some work on second law and this issue of entropy and the second law. And that was done again with Amilcar and Sachin Vaidya in CHE. Okay. So what do I do? The construction I am giving here is coming actually, if you know group theory, and so group theory is for say finite dimensional groups and Lie groups, for say compact Lie groups, are part of the tools of anyone who is trying to enter quantum theory at any level. And one of the fundamental things we learn is we just don't learn group theory as a set of tables, but try to go a little bit deeper, finite dimensions, or compact Lie groups like SU3, SUN, and so on, is what is called the character theory. Okay. So one knows that the characters completely determine the representation of the Lie group. Okay. Now it also happens that the characters can be used to define a state on the on an algebra which you can create from the Lie group, okay, and you can recover the entire regular representation of the Lie group using the character and this naturally defined algebra coming from the group. Okay. I will not go into it. I mentioned this fact. So this whole development seems to be taking part. It has its origin in this part of the game, and apparently Naimark was working on all these things, and they seem to have gotten together to develop this idea. Okay. So the idea here is already known, probably known to people like Frobenius or Lie. They must have known these ideas, but they did not adapt it to algebraic state. So what do? I take this omega and I want to create a Hilbert space. So what I do is to each element of the algebra, called alpha, I associate a ket vector, they call alpha. Okay. So I label the kets by this alpha, where alpha are elements of the algebra. So I can, if you take linear combinations of alpha, these vectors also add accordingly. So alpha plus beta, the ket is alpha ket plus beta ket. So that is a vector space. But what is a scalar product? I need a Hilbert space. So what is a scalar product? But I told you that this omega is a positive definite of, but it gives omega of alpha star alpha is positive. So let me use omega itself to define the scalar product. You set the scalar product of alpha with beta as omega acting on alpha star beta. Okay. The omega of alpha star beta is a complex number, but if I take beta equal to alpha, this is omega of alpha star alpha, this is non-negative, which is the fundamental property of a Hilbert space. So you have got a scalar product. Can I convert it into a Hilbert space? Yes, you can. Modulo technical issues like completion, there's one problem which I just mentioned. It could happen that there may be alphas for which omega of alpha star and alpha is 0. It could happen, for example, the density matrix may be a projection operator on certain set of vectors, and if the alpha you take happens to be 0 on those projectors, then omega of alpha star alpha will be 0. So you will have a non-zero vector in the Hilbert space in the algebra with 0 norm. So that there's something is wrong. You cannot have a 0 norm for a non-zero vector. So what do? So the technique for removing this single problem is write down all the null vectors and you coordinate it out of it. So instead of considering A, you consider the equivalent classes of A modded by N. So the element of A mod N will be, which I denote by alpha tilde, will be alpha plus this whole set of null vectors. So you are now dealing with not alpha, but alpha plus the set of null vectors. So now you label the vector not by alpha, but by the equivalence class containing alpha. We put it then one can easily prove that we don't have this problem of null vectors. And I have to tell you how these alpha act on these vectors. Well, that's very easy. You take alpha and multiply it on beta bar, beta equivalence class. You go and multiply beta, alpha beta, take the equivalence class. You multiply and then take the equivalence class, and one proves that it is well defined. That is, equivalence class is not, this equation makes sense. There is alpha beta equivalence class is alpha equivalence class times beta equivalence class. You can easily prove. So this is a consistent definition. So this gives you a Hilbert space where the vectors are built on alpha ket vectors of this kind, and the scalar product is given by the density matrix itself. Now, the special, I'll give an example now, but the special case where there are no null vectors is of particular importance, because in that case, again, some of you I'm sure are involved in this. You get this whole business of Tomita Takesaki theory. So, I know that Jalan was talking about it yesterday. So, in case where there are no null vectors, some very much more rich structure emerges. And typically, for example, the vacuum, alpha vacuum. So, if you try to do this and look at the Fock vacuum and look at local algebras acting on it, that is a case where there are no null vectors. So that is a case where the n is 0, then some very rich new things start happening. So you should keep that in mind. And there are examples I can give in finite dimensions, but I can tell you what the whole Tomita Takesaki whatever is in finite dimensions. It is not difficult. And it also has turned up in finite temperature field theory. And this doubling, some of you know, the doubling on the Hilbert space due to Umezawa's doubling of the Hilbert space to get a finite temperature field theory. That is exactly this Tomita Takesaki theory. He may have known it or not, I don't know. But it is exactly that, and Ojima has written a paper explaining how it is so. So, yeah.
Just a clarification, the Hilbert space that you're talking about here is the actual Hilbert space that we have to point out.
Yes, I'll show you exactly. Yes.
Just the space on which the top operator will be the same thing.
I think you use space time.
Not space time. The space of space or the alpha ket vectors on which the operators are acting.
Yes, it's exactly the same. The entire operator theory can be imported. Okay. And the only technical issue which is important is this is not, you're going to set of vectors which have a scalar product which is positive everything, but it may not be complete. There may be Cauchy sequences which may not convert with the space. So, yeah. Correct?
What I don't understand is that you started by saying that the Hilbert space is fundamental or something, but how are these two pictures then different? That I can say that I start from some Hilbert space and then I look at all the operators that are well defined on it. Or I can say that I start from operators and then I look at the space on which these operators can be represented on.
Yes.
it looks like these two are just equivalent. So how is it that this picture is different or more fundamental than these two?
I would not say, maybe I should not say. So, certainly, this activity is here at this level. So, in quantum field theory, as I told you, local quantum field, some structures emerge which may be representable in terms of in this language, but certainly in quantum mechanics, this is not a challenge to standard quantum mechanics at all. Is that the claim here that is made is that it is conceptually clearer in our heads on what is happening. Okay? That is all. That is the thing that I will say. At least it is to me much nicer to say that classical and quantum mechanics are two aspects of the same thing that we do all the time. And so happens in quantum mechanics that something new happens. There are more emergent structures which, unlike in classical mechanics, okay, which are purely mathematically characterized, but which express the same data. Okay. That is all I should. So I did not. I want to communicate is only that information.
Is there any baggage that is being avoided in this?
So again,
Any baggage in the concept that the system that I'm familiar with, people space, probably, can it be avoided by this process?
Correct.
Why
it happens in certain cases. For example, for magnetic monopose, charge monopose system, that if you try to write vectors in a Hilbert space, you get into trouble. There are no, for example, there is no wave function of this scattered. So suppose you have a charged particle in the monopole interact. I am giving you an example where something twisted happens. So you write the classical Lagrangian, no problem. But if you try writing a wave function for the charge monopole system in ordinary quantum mechanics, your wave function, you cannot do it unless you introduce singularities. But in the language of the states on that algebra, you can easily do it. And essentially, that is what, if you read the Dirac paper differently, you see that is what he is doing. Okay? So he is passing from the language of vector states to density matrices. So in that case, there is a definite advantage in working with density matrices. Okay? But can I do everything that I do in density matrices using wave functions? I think most of it we can do. Okay?
So basically, you're putting both of the theory, classical and quantum, in similar format. It's just that when you have quantum, you have a non-commutative algebra.
Yeah.
Whereas there you had a commutative.
Yes.
Now this one, yeah. So I have a question. So so what about the Hilbert space that you get by doing this? Is it separable? Guaranteed to be separable?
Well, it's a good question. From what I know, so if the algebra is some huge system, say fundamental algebra and so on, my knowledge is limited. From what I know, there are what they call normal states. There is something called on these states, what is it called, subadditivity property, which is basically some exchange or some integration. So you get a sequence of vectors alpha n converge into some alpha in the topology given by this omega state itself, converges, you should be able to take the limit outside. So it's interchange of limits. Omega of alpha n going to infinity within omega must be equal to n going to infinity omega alpha n, such things. No? So the interchange of limits, there are some conditions like that. They're called subadditivity properties, which if they are fulfilled, it appears that you always get separable Hilbert spaces. If those fail, I don't know what happens. I have asked related questions to both Vijay and Sundar, and it seems that Vijay has declined to answer. He says he doesn't know this kind of analytic issue. Sundar has promised to think about it. So there are difficult questions, but there are physical relevance. Okay.
So you got a representation of an algebra which is acting like the set of linear bounded operators or actually.
Yes. On a Hilbert space, and in the standard cases, it will produce standard answers. I find this a nicer way of thinking about it. Okay. And also, it gives me a way to enter the field that other people are doing. Okay. Some other people are doing.
Can you comment on this rich thing that happens when you don't have these null states? When this, you said some rich phenomena occur when you don't have null states.
Then I will show by examples. This is the what happens is okay. Here I have an example. So if you don't have null states, okay, group theory, you may know that if you find a regular representation of a group, what we normally take to find the regular representation, say, let's take finite group. Okay. So we convert the elements of the group into a vector space. So you take a regular finite group is G1, G2 up to Gn. Gn is the order of the group. You take complex linear combinations and make it into a vector space. Okay. Then the group can act on the left of it, okay, or it can act on the right of it. To act on the left of it, you get the left regular representation, and we know that in the left regular representation, you get all representations of the group. If you're reducing it, you get direct sum of all possible irreducible representations. But on the right also, they commute to the left action. So the left representation I have got has a big commutant things commuting with it coming from the right. Okay. So there is a degeneracy of each representation, and that's equal to the dimension of the representation. Yes. So in the regular representation, each representation of dimension n as a d occurs d times because of the right representation commuting with the left representation. And this gives you the famous formula that if you sum over all d squared, is equal to the order of the group. You must have seen the formula. If d is the dimension of a irreducible representation of a finite group, summation of d squared is equal to the order of the group. Okay. This is used to very much to tell what are the allowed dimensions of the representations. For example, for S3, you can easily check that S3 has it has it is 2 into S3 is 6, no? So I think two one-dimensional representations and one two-dimensional representation. Okay. So that's a unique solution to the number theoretic problem. That write 6 as sum of squares of integers, and you will positive integers, you get only 1 plus 1 plus 2. Okay. So 1 squared plus 1 squared plus 2 squared is 6. Okay. So that tells you that there is one two-dimensional representation and two one-dimensional representations. So that is used quite commonly in character theory to find the dimensions of the representation. So that happens in infinite dimensions. There are no zero modes. There is no null vectors. The Tomita Takesaki theory tells you that there is another algebra. You can find. I can write it in finite dimensions. I can show all the steps of the calculation. It shows that the algebra A has a commutant, is written as A prime, let us say, okay, as I move into A, as big as A, okay, exactly as in groups, okay, huge. A is infinite dimensional, A prime is infinite dimensional. Okay. What is the A prime? So you may ask, what is the A prime in quantum field theory? So you take Riller wedge. I wish the people doing the Riller wedge were here. Okay. The quantum fields in a Riller wedge is some infinite dimensional space. Okay. And it can act on some vacuum state, and you can find its representation. So what is A prime in that case? In that case, A prime are all take the Riller wedge and take this causal complement, then go on the other side, it is also a Riller wedge. So A prime is the algebra, this causal complement is also infinite dimensional. So the recognition that this commutant is coming from the Tomita Takesaki theory is exactly the same as the causality requirement in quantum field theory is very important. And it was done by Balachandran and Wickman long ago. And they did not know. The Tobita theory was not well known at that time. And much later, it was recognized by Sivan, I think, that this is the connection, and Haag reports on it at that time. So,
Commutates are treated with causality.
yes. So,
Then,
sorry.
no, is it true in general that if you take the commutant of an algebra, you get a set of operators?
No. No, it's not. That's not correct. If no, there are exceptions. If you take an algebra A in some local region, and you take the take all operators commuting with it. So take all operators commuting with it. Certainly, they will contain all operators in the causal complement of the space-time region you're looking at. Are there more operators or no? They exactly are the same. It's called half duality. So half duality is true in many cases, but not always. And one knows counterexample. So that fails, something else also will start failing. Some other research that we know from standard quantum field theory will start failing. So people have written examples where half duality fails. So that is not true, but it happens in the Balachandran and Wickman case under appropriate conditions that this coincidence is happening. So what they showed was that this comet April, in the case they were considering, that is the case of massive scalar fields, they actually computed it and found that they were the same. So for them, this going from A to A prime was the CPT operation. So they used CPT to go from one level, then checked explicitly what is CPT comes here as some anti-linear involution of Tobita and Takesaki. So you may look mysterious. If time permits and there is interest, I can show you how it is done in finite dimensions and how it goes into this finite temperature field theory. So this is something we know in some other language. But the structural research that there generalities come out here. So I think I see people peeping. So I'll do 5 more minutes and I'll stop. I think there is a seminar at 3:30. If I'm not wrong. Okay? So I'll stop there. So just want to look at one example, 2 by 2 matrices. Okay. So let me take 2 by 2, take 2 matrices, and I will take all 2 by 2. So my observables are acting on a 2-dimensional vector space, and the observables are given by 2 by 2 matrix. And the star operation is Hermitian conjugation. The standard Hermitian conjugation is star operation. And I had to write a state. Let me write a state. The properties of the state is on the identity should be 1 and it should be positive. So what I will do is to take omega lambda, I use a parameter lambda lying between 0 and 1, and I will take this lambda alpha 1 1. So omega lambda acting on alpha will be alpha 1 1 times lambda plus 1 minus lambda times alpha 2. I take this state. You can see that alpha 1 1 and alpha 2 are 1. This omega lambda of 1 is 1. Okay. And you can check that if you calculate omega lambda of alpha star alpha, it is non-negative. This is trivial calculation, and you check that it is that condition is also fulfilled. So there are no null states. Okay. So what is a Hilbert space? Every element of the Hilbert space is given labeled by 2 by 2 matrix. Okay. Exactly by the 2 by 2 matrix. So how does beta acting on a state like this? It acts by left multiplication. So in this case, beta will act, say, on all matrices on the first column, second column is 0, plus similarly for the second column. I write like this because the vector space spanned by entries like this with the second column 0 is invariant by the action of beta, and likewise in the right one. So the representation splits into 2 parts. Okay. H1 plus H2. Okay. So you see the multiplicity happening. This is the multiplicity I told you about for group representations. It is the same thing. It's coming because I can act on the right by the same matrices, okay, on this alphas, we multiply by something on alpha and then right, the action of beta will not be disturbed. So there is a comitant. That is a reflection of this multiplicity. We'll come back to this multiplicity in a minute. So what are the norms? I think you compute the norm. Using the omega, you compute the norm. And you find that the scalar product of alpha 1 with alpha 1. So by alpha 1, I mean the one with the second column being 0. And by alpha 2, I mean the one with second column being first column being 0. I compute it. And you find that the norm of alpha 1, lambda times alpha 1 squared plus alpha 2 1 squared. And the second one is 1 minus lambda times similar thing. And you can see that they are not equal. This is important, it is not equal. And furthermore, you see that I choose lambda to be 1. You can do that. Then the norm of the second column vectors will be 0. So there will be null vectors if I choose lambda to be 1. Okay. For the moment, I want to avoid it. But I can do it, but then you get a different representation of this algebra. So this is an example of this null space I told you, and you can discuss this also. So, it's up to you. You're choosing a state, so you choose any number between 0 and 1. For each of them, you get a particular. So, in this example, I have one parameter family of choices. There may be more, but I took just one set of states labeled by lambda. Each of them will give you a different representation of the algebra observables. Nobody said that density matrices are unique. So it is not unique here. Okay. Okay. So given this, I want to go, I will just tell the problem now and come back next time. I want to go into the issue of entropies. The problem is the following. Classically, the entropy is defined by rho is a function, takes place probability density, and I write the entropy is defined, can be defined as minus dqdv, the volume form on the phase space, times rho times log rho. Rho qp times log rho qp. I can integrate and get an answer. What do we do in quantum mechanics? The fundamental proposal is it is minus trace rho log rho. First issue, just to clarify, what do I mean by log rho for an operator rho? What do I mean by that? You can do that. You can define it in many ways. The standard way is to use what they call spectral calculus. So you take the eigenvalues of rho, right? Rho in terms of projection operators and eigenvalues, and you take log to be logarithm of the coefficients, the eigenvalues. As you will see explained in full in Interact's book, okay, there is a whole section on functions of operators. He's actually writing what is nowadays some fancy people call it as spectral calculus. He has got it in his book, so you can read it from there. So okay, I got a formula. What is the problem? The problem is the following. There may be many rows. We have already seen that there are many wave functions given the same row. But who told me that there is only one row which will be the same state? Okay. So suppose I have many states, many rows, all of which have the same trace on my algebra. Are these entropies going to be the same? And are there cases where there are many rows? The answer is yes. There are cases where there are many rows. In fact, this will happen every time you have this no null vector case. Every time it will happen. Okay? And if you compute the entropy, you get generically you will get different answers. Okay? I can see somebody he is getting restless. Okay, so I will show this next time explicitly, but this is a fact. This is what happens. That there is no uniqueness in the mapping of a state. State is not given by rho. Okay? It's given by its values on the algebra of observables. So you may have many rows giving the same state.
These rows are not 10%, 90%.
No. Otherwise, the density matrix, no. they are different. They are actually different. I write formally, they are different. They are given by what we will see, or what are called stochastic maps. So they are given generically irreversible maps. The maps which take you from one road to another are generally irreversible maps, even in finite dimensions. And Kolmogorov has already developed entropy, uh, stochastic dynamics for infinite dimensions. So you will end up by getting stochastic maps, and the entropy will also keep increasing. Not only will they not say the same, but they will increase. Very much like what you imagine, our friend the Boltzmann imagine. They will go every time you look and update your row, the entropy will increase. Is it dynamical? I don't know, but this is what happens due to theorem due to Jensen. So it's a theorem. So it will go on increasing.
There must be a set of omegas such that you have a unique path from omega to a row up to a similarity class. Set of such states.
Yeah. So the underlying set of states. So you're looking at not all, let us say in finite dimensions, you consider all states which have no non-vectors. You can do that. The issue is you can suppose, and they are finite, you can write. So this rho omega is called a convex set. That is, you take, suppose omega 1 is a state, when omega 2 is a state. I don't know how to write it. Then lambda 1 omega 1 plus lambda 2 omega 2 is also a state. If lambda i's are positive and they sum to 1. So they form a convex set. So if this convex set is what is called the simplex. So I will show you pictures of simplexes. For example, triangle is a simplex. Then in the case of simplices, this problem will not occur. But if it is not a simplex, for example, the block sphere is not a simplex. This also already for one single spin, one qubit, this problem occurs. Because the center space now is the block sphere, and the extremal points, the edge points, are the boundary, and there are infinitely many of them. And you can put anything in the interior as a convex combination of two things in the boundary in a huge number of ways. Right? The vector here, take another vector here, add them, even orthogonal. So what happens if you compute entropy? They are different, and you have this problem that it will go on increasing every time you change. So this is not a trivial problem. I'll show you actual examples. I would say that the implications of this statement, I do not know. I do not.
That example will be.
I'll give examples. I will give examples. Then what happens to the thermostat, KMS states? Can I have a mixture of objects in thermal bath? Is there a unique entropy identifying? All these issues come up. Okay? And they have been addressed by people like Lee and Hard and so on. In some cases, yes. In many cases, no. The cases where it is not possible, what is the interpretation? Is there something richer going on? I would say that I don't know. In fact, as I told you, Longo has just now written a paper bearing on these issues. And I don't know so much physics or mathematics about the Longo. Okay. Yeah, I would say there are many issues to think about there. Let me put that.